Actually really rare these days. Well, I think we can start early. Welcome back, everyone. For our work today, we're going to be in section 5.2, but we definitely should talk about the exam and where we're at with the grading on that thing. I have to admit to everyone, I'm pretty behind this week. We're just kind of getting through it. I don't think I'm going to be able to have it completely graded to return on Thursday's class. But on Friday, that's going to be my first order of operations. I'm going to start by grading, and this will be the first class I grade for. I'll be grading the exam 3, and you could probably expect your solution or your grade on exam 3 to be posted onto Moodle probably sometime on the afternoon on Friday. I'm going to try to make it sooner than later. And just in case if you're really wondering about that grade, I'll also mass email the class once the grades are actually input, so you don't have to feel the need to check Moodle a bunch of times. You can just watch your ISU email, and then you'll know exactly when it's been put in. And also I want to mention, I think someone pointed this out in class right before taking the exam. I think it was you, Don, but I'm not totally sure. Exam 3 was really unfortunate in that it landed right on daylight savings time. I didn't think that'd be a very big deal. I didn't even know it was coming, but I didn't think it would be a big deal until we were all there on daylight savings, and that is actually kind of hard. So I'll find a way to make it up to folks. That wasn't the easiest exam to get through, for at least that reason as well. Well, any questions or comments so far, folks, before we get started? Yeah. Oh, yeah. This one will be due on Monday, yes. Yeah, so thanks for reminding me about that. Yeah, if you were focusing on exam 3, that is a pretty good strategy. So we should be punished for doing what makes the most sense. So this due date is extended, absolutely. And I did want to mention to the class, there's been a lot of issues of, say, tragedies, sickness, things like that, problems. I've been giving people the opportunity to make up assignments that they just missed for one reason or another. And so probably what I'm going to do is I'll announce this officially, but we can just say it right now. If there was an assignment that you didn't get in, that you missed, that you would still like to complete, I will still accept that assignment. So at this point, due dates in this class, they're really more about pacing so we don't get too far behind. I'll make that an official statement. Let me make sure I remember to make that an official statement. Okay, I got my reminder in. I'll make that an official statement, probably somewhere here around Thanksgiving Day. I'll just call it extra credit opportunity. If you have extra time, go back and work those old assignments if you missed any, and I will still accept them. If there was an old assignment that maybe you completed everything and you just want to rework something, I would accept a reworked assignment as well. Again, I'll make that official so that the language is a little bit more clear, and we'll have more opportunities to ask about that. But any questions at the moment? Yeah.
If we had an assignment that we didn't do very well, and we could redo all those problem lines and turn that in and get a higher grade.
Yeah, exactly. Okay. I'll accept a reworked assignment as well.
Okay.
And I wouldn't necessarily make you do the whole assignment again. What you could do is take your old assignment and just do the problems that you did rework, staple it together so I know how to regrade and things like that. And that would qualify. That way you're not solving things you already are really certain about.
Okay. Thank you.
You bet. Well, I guess we're about ready to get started. Any last questions so far, folks? Okay, so we're going to section 5.2 on the definite integral. Oh, and I still have to open those notes. Let me get right inside there. And here's how it's going to start out. It doesn't start off exactly with the definite integral, but this is a good time in our course to kind of pause and talk about the big concepts in calculus so far. because we're stumbling upon the third big idea. Our concepts have been continuity. Didn't really get its fair share, but it really is truly important, probably the more important concepts out of all of these. Next one we went across was differentiability. And this one is going to be the new one that we're about to define on these notes. The integrability of a function. Strange words. Every one of these concepts comes out of a limit, some way, somehow. And so it turns out in calculus, it's all about knowing how limits work, how they operate, and how they define all of these new objects. And because that's such an important concept, you can expect that questions like these are going to appear on the final exam. I may not ask every single one of these, but it's common to see a question about continuity re-expressed in the form of a limit or differentiability. That's all. This is our opportunity to practice before we look at how integrability is also a limit, all at the same time. Let's start off with this. It's a statement that f is continuous at 3. And the hint on this one is continuity is really all about direct substitution. So the limit statement here would be the limit as x tends towards, we're talking about continuity at 3, so we need to send x towards 3 of the function f of x. It would go like this to start, but then direct substitution says, if this function is continuous, and they just said it was, doesn't matter how complicated or convoluted it looks, we're just going to take f at, excuse me, 3, and that's what continuity looks like in the form of a limit. It means you can directly substitute in a value and always get the correct expression in the limit. So that's a wonderful statement right there, but it's easy to forget about these things because this is like 2 months old material already. Any questions at all, folks, with that limit there? Okay, this one is kind of tricky, but it's really fast to do. This one's a little bit trickier and a lot slower to do, especially if you go this route. I think this one is best as a two-step process. We want to write down something that involves differentiability. Oh, geez, I have the wrong color coding here. Sorry, let me make sure. Let's just kind of go like this. Sorry, I have a weird color coding issue. Continuity, let's keep to green. Differentiability, let's do blue, or else the notes are just going to be hard to read at that point. So right here, they gave us something that involves a derivative. Here they're using Newton's prime notation. So we would write out to start in step 1, f prime at any number x in the form of a limit, or through the definition of the limit is limit as h goes to 0, f of x plus h minus f of x, all divided by h. So that's the definition of the derivative at any x. Then on step 2, to answer the question, here's what we'll write next. The equation f prime at 3 equals 9 in the form of a limit turns into, go over here and just plug in a 9. It's the limit as h goes to 0, f at 9 plus h, plug another 9 right over here, minus f at 9, all divided by h. And both of these limits, the original one right here, it just came from the formula of a slope when we were looking at slopes of tangent lines. We took a secant line, made the value of h get smaller and smaller, and so the point f of x plus h and f of x got closer and closer to overlapping. Or in other words, you're getting closer and closer to dividing by 0 in the denominator. So this, well, it's almost there, but it has to be an equation, so we write equals 9. That last bit, if you did forget, is not huge, but it has to be an equation, so it does have to go in there. Any questions with that limit there, folks? Okay, so it's material again from way back in chapter 2. I think this one was section 2.5, and this is 2.8, 2.7, 2.8. It's getting a little foggy. But now we're talking about integrability. Here's how we can now define this thing. We need another kind of limit. I'm just going to start through this definition. Let me fix the format here just a little bit. First thing we need to do is just come up with the function. So let's just draw a really fast sketch here. I'll emphasize quadrant 1, quadrant 4. because this time, let's let our function dip below the x-axis this time. We can start it off at A, go off to B. The function can begin above the x-axis, and then let's let it go like this. So here's y equals f of x. So we have a function f defined for x between A and B. So we're at that part of this definition. Next thing we do is we divide the interval, that closed interval from A to B, into n different subintervals of the equal width delta x. So that's our delta x formula that we're worried about now. Delta x by formula is this b minus a divided by n. Once we have that delta x, that's just the equal width between all these boundary points right here. Let's draw them in as best we can. So we'll have a to start off as x naught. We add the quantity delta x to get to the next value. I'll just place it here, x1. Here's x2. After adding delta x again, x3. And let's let our b be x4. So the graph that we're dealing with is going to be for n equals 4 in this problem. But we're not content with n equals 4 because what we're trying to do is integrate this function. We're not trying to find necessarily the same kind of values in the last section. In the last section, we insisted the graph be above the x-axis. That way, we could talk about the area under the curve of that function. We still are dealing with areas, but now here's this new situation. From here to here, all of this is positive area. So we'll think of that as a positive quantity, and all of this down below over here, I should use a different color. Blue is already taken. Let's go with, how about purple's a good one because this is the new concept now. All of this area right here is considered negative area. So when we integrate this function f of x, we're finding the net change in area. From A to this point, we have positive area. Then we subtract all of the area when we integrate from here to here. In net, it's going to end up being positive. There's more area above than it is below. And if this was a velocity graph for, say, a car, this means we're going towards the right in distance with positive area. Then velocity became negative. We switched directions. This will be distance going to the left. If you think about that first problem with areas we did with velocity and distances. So signed area is definitely something we want in a physical process. It'll give us more information about a problem. So now we have a picture where n is 4. And here's what we're going to do next. We're going to take sample points in every one of these subintervals. A subinterval we like from A to x1 or x1 to x2, and so on. We'll pick a generic sample point, and they could be anything. It could be a left endpoint, a right endpoint, or a midpoint, or just something else. Let's just put down some things generically like this here, just to get a visualization on our graph. So these will be our sample points. And geez, I guess we need a new color. It's really easy to run out of colors eventually with this kind of stuff. Red seems kind of aggressive. Is that readable? Does that look right to folks for readability up there? Okay, let's go with red just because we're running out of colors, no other reason. So for our first subinterval, we can take it to be just a generic midpoint. It's allowed. So this would be x star 1. It gives us a height right up here, and that height is going to determine the height of the entire rectangle, this very first one I'm attempting to draw. Then we put in another value, x star 2. The way these are chosen might be in some systematic way, or they could be just chosen fully arbitrary. Let's maybe take something right around here. This is just an arbitrary choice. So this one would be x star 2. It gives us a height right here on the curve. And so now that's the height of the next rectangle. Maybe that wasn't even a great choice because we've underestimated the area by the red dot, but that's okay because this is just the picture for n equals 4. That 4 is going to increase when we integrate this function. This is just one step on the way towards the total integration of this thing. Next one we could pick, just because we can, let's emphasize x star 3 could be a right endpoint. I'm picking it to be x3 itself. We would get a height that goes right here, but this height is below the x-axis. That's why we're getting negative area on this. It's just a mathematical consequence that f at x3 takes a negative value below the x-axis. So this whole rectangle going from here to here is now negative area being thrown into the problem. Then last one, let's take a x star 4. I'll just put this one generically right here. The height of the rectangle would be right here. So we would come down and around. And these rectangles in red are attempting to take positive area and subtract the negative area. At n equals 4, it's not going to do a great job, but the computation, let's say the approximation, of what we're calculating is really the definite integral of f. So the approximation of the definite integral of f becomes better as n becomes large, but I'll express n becoming large as n goes to infinity. So that's what we really would like to do for integrating. We have to take the limit of the sums of the positive rectangles and the negative rectangles, and we'll get more and more of them as n goes to infinity. So imagine this picture with, say, 100 different rectangles. It would be really hard to even see the width of those things. It would almost look like you're looking at the curve that's coming down. At 1 million rectangles, the resolution of this monitor wouldn't even be able to show what's going on. You'd have to start zooming way in on this thing. So that's the picture of what we're trying to convey. And finally, this is the definition. When we say the definite integral of f, this is what we're referring to. That object right there is the definite integral of f. Its computation is by taking this limit. As n goes into infinity, that's just asking for the number of rectangles to become large. But then we have this summation, which is confusing. Let's expand this thing to get a better feel for it. Oh, the highlighting doesn't follow, does it? We put that over here. This notation right here, referred to as summation notation, is just a shorthand. When you see that, it's the same as writing limit as n goes to infinity of all of these objects, f at xi star times delta x. That's referring to, say, if the I is 1, taking this rectangle. I starts at 1 from down here, and it goes up to n, the last value. But n changes because we're taking the limit as n goes to infinity. So we're asking for more and more rectangles in this process. And so over here, I have to go plus f at xi star. Oh, I did make a mistake here. Sorry about that, folks. Let me back off to this location. That should have been an f of x1. I starts at 1 and then proceeds upwards until we get to n. Sorry for that mistake right here. Let me highlight it in yellow. And there's a star in it. So let me just pause for any corrections folks are making. Sorry to everyone working in pen today. Okay, so with the 1 to start, because we're starting at 1 from the index here, we'll go f at x2 star delta x, and then keep on adding until we get up to n. N could be a very, very large number. It is going off to infinity in the limit. So the best strategy here is to go plus a little bit of a dot, dot, dot to say, and so on, until you get to f at xn star times delta x. Now, you can factor delta x out of the whole thing, but the goal in writing out this is just to get comfortable with that is saying. Think of this summation symbol right here as really just saying add a bunch of stuff repeatedly over and over again. Well, any questions at all, folks, on The definite integral so far? Yeah. Oh, the star itself is saying it can be any sample point. So x star can be any number from xi minus one, that's like x1, up to xi, like the x2. So the x star just means you can pick any number from here to here. Does that make sense there? Gotcha. Other questions so far? Yeah. For the summation notation here, it would come into play really from the delta x is where it comes into play. We have to involve the a and b into this formula right exactly there. So in this location, you'll have b minus a divided by n, so the width of that delta x goes to 0 as n goes to infinity. But does that answer your question about the boundary points? Awesome. Other questions or comments so far? Okay, thanks for these questions so far. This is exactly the right questions you want to ask about this stuff. This is a very new topic, it feels like all of a sudden. But before long, in section 5.3, it's going to feel awfully familiar once we see the fundamental theorem of calculus. Well, that's the setup so far. The definite integral is written in this way. It's like an elongated S. And the reason for elongated S, it reminds us, it's a summation, really. It's a summation of the limit of these approximating rectangles. And this is such a common approximation that this thing has a name. Let's find a color to highlight it. This whole thing right here is a Riemann sum. So we can say now a definite integral is the limit as n goes to infinity of your Riemann sums. If that limit exists, we'll say the function is integrable. If it doesn't exist, we'll say it's not integrable. And it's named after good old Bernard Riemann. This guy lived about, well, quite a while ago, but it's still considered modern mathematics, even though this is a while ago. And he pioneered a lot of these methods. The German mathematicians seem to have lots of major results. Another one is Leibniz himself, who independently discovered calculus.
That's all the names that are difficult to get. So
I agree. Yeah. L'Hopital, yeah. Yeah, it's pretty much just saying it incorrectly in front of my instructor as a student that kind of pounded it into my head. Yeah. And we see a lot of other ones, like, for example, this guy is probably the most prolific mathematician of all time, and it's pronounced Euler for some reason. Other questions or comments so far? Probably. If you step outside of this classroom and go look to the far left hall and the far right hall, all of his tomes and manuscripts he produced in his lifetime would extend all the way across, probably. There's an actual project to try to digitize everything he put out. You can look at his tomes of information he's put in. He's the guy who discovered this number. And it got named after him. That's Euler's number. So Leibniz, Newton, they're great guys, but the world really wishes they were as prolific as Euler was. He was something else. He went blind and he still produced mathematics. He just had his assistants notate for him. Well, other questions so far? Okay, well, we've got something kind of wild, kind of crazy looking, and it involves lots of notation. That's something we're expecting because derivatives themselves have lots of notation that we have to get used to. So that's what this is all about, right down below here. So when you see this symbol, we're thinking about the integral sign. And again, it's just an elongated S is what's attempted to be written as. There's always going to be a decoration, a lower bound and an upper bound, if you're doing a definite integral. We'll take those off if we're doing an indefinite integral. All that will be is an antiderivative. So the lower value A, the upper value B, we think of them as the limits of integration in this problem. And there's another weird looking symbol here, dx. What is dx? Well, it's part of the integral sign altogether. Think of that dx as similar to when you write out y prime equals dy dx. The dx down below tells you differentiate with respect to x. And the x here tells us to integrate with respect to x. And there is a connection from a really long time ago. If you write y equals f of x, the differential of y is dy equals f prime of x dx. We're going to see that connection even more strongly in section 5.4, where we actually use the stuff, the differential, for the first official time when we're doing the substitution rule. The differential and the substitution rule are just trying to undo a chain rule process, reverse it entirely. So that dx you see here is like the dx you see right over here. They're not exactly the same, but it's a very close analogy we'll take advantage of in section 5.4. So next thing we need to discuss about notation is you'll often hear this word, the integrand, a lot of times, and it's always referring to the function f. So anytime you're thinking about the integrand, it's the function going inside. The thing on the right, like we mentioned, this is the Riemann sum, this portion here highlighted. And when we take the limit of it, we're doing the limit of Riemann sums. And that's the limit definition of the definite integral finally. So lots of notation to get through. And I thought, because I also assigned it as a homework question, this is a good place to pause for a bit and talk about, oh, I had something else here. I was going to talk about doing a midpoint rule once again, but we'll pause here because I forgot I put some white space for a purpose, and then we'll take a look at a midpoint rule. So we have nice theorems that we would like to talk about that helps us decide if a function is integrable or not. Integrability means a very complicated limit would exist. Those are really hard limits to check though. So we need some methods to help us out. And this is what theorem 3 says. If you have continuity, and it has to be continuity on a closed interval, so bracket a to b, including the lower boundary of a and upper boundary of b, continuity there is enough to guarantee integrability on that closed interval. So continuity turns out to be really impressive with a lot of our theorems. It seems like a small concept. The limit definition of it is not that impressive. It's really fast to write. But continuity on a closed interval is an extremely important concept. That alone guarantees integrability. And there's this catch-all right here. If continuity breaks by a little bit so that you have a jump continuity, or at most finitely many jump continuities, it's still integrable. Let's write down a couple pictures that just captures both of those situations. In this picture here, if we integrate from a to b, and the function looks like this, then one thing we can say right away is this function obtains its absolute maximum and its absolute minimum on this interval from a to b. That's part of the hint of why it has to be integrable. Already it's easy to estimate the area using its absolute max and absolute min. You'd have an upper bound of area. You could take, say, this area as a box. That's way overestimating, but it works. You could use this as a lower bound for area. That's a massive underestimate, so it works. But then what this tells us is there is a finite area there that we can really find. And that's just because we can find its absolute maximum and its absolute minimum. This is a concept all the way back in from section 4.1. So here we can say, if this is our f of x, f is integrable since f is continuous. Meaning continuous on this entire interval, but only continuous from the right at that boundary point, and at this boundary point, only continuous from the left. There's no other portion of the curve for continuity. So we can integrate this, and in other words, that means the definite integral from a to b of f of x dx exists. There's a number there, and for this function I drew, it would represent the area under the curve bounded by the x-axis. So we can now see just by looking at the function, if it could be integrable or not. Then we go to this fancy statement here. This doesn't affect our course a lot, but if you're taking a lot of calculus and you know you're going into elementary analysis, possibly real analysis, you might stumble across this concept right here. If f has only a finite number of jump discontinuities on a closed interval, then it would be integrable. But that begs the question, what would a function look like that had an infinite amount of jump discontinuities on a closed interval? Those functions do exist, and they might be kind of hard to plot. So if you're curious about those, I'd say that's a pretty fun Google project to take a look at it. Or you can let me know if you're curious about it. I can do some research and just throw a document on the website, somewhere on Moodle. The thing about functions is that you will always see weird statements like these on some of the theorems because functions are very, very strange. It's a very vast landscape, and we only get a feel for it once we talk about new properties like continuity, differentiability, integrability. So I'll attempt to draw one with finitely made jump discontinuities. Infinitely many is not easy to draw. It's going from A to B. And so this function, that was meant to be an open dot. This function is not so bad. So it does have a domain from A to B. It's defined on every number between A to B, but it's not continuous there. However, there is 1 and 2 different jump discontinuities. And so we can say, since f has, let's just say finitely many. Finitely many jump discontinuities, but is continuous otherwise, f is integrable. And that means, once again, the definite integral from a to b of f of x dx exists, even for this strange graph. And you can kind of almost imagine why it should exist. If you drew, say, a line that went from here, a line that goes like this, then you can find the area of every one of these different regions in just a straightforward kind of way. It seems plausible it really should exist just by looking at this graph. Well, yeah, let's leave that on there for our official upload on this thing. So that's a really powerful theorem. Ordinarily, the way we use it is we just observe continuity overall on the closed interval. And this is something that can happen, but still allows us to integrate. Any questions at all, folks, about any of those diagrams or the theorem? Okay, then again, this is where I was mentioning, after talking about continuity, differentiability, and integrability here a whole lot, it might be nice to do one more midpoint rule. I did assign one in the homework, so my hands are kind of tied. We should do one regardless. But doing the midpoint rule again is a good idea. It's a tricky rule in section 5.1 otherwise, or either way, so it's a good one to do a second time. And now we have more notation, so it kind of feels like a new problem. It says find the Riemann sum for f of x equals sine x as x goes from 0 to 3 pi over 2. We'll use 6 terms. This is a good point to write n equals 6. We'll take sample points to be midpoints. So we'll use m for midpoints, m6 to say with 6 subintervals. And we'll also sketch a graph as well, just to show what's going on. That's probably the best place to start. Let's begin with the integrand, f of x equals sine x. So we have a function that's going from 0 to 3 pi over 2. Sine takes both positive and negative values, so that ought to be a good graph again. So here's positive 1, here's negative 1. The sine curve starts at 0. And I guess I'm going to need more key values here. Let's go by units of, how about pi over 2? Probably makes sense. At pi over 2, it obtains its maximum value. Add pi over 2 again to get pi, it'll hit the x-axis. Add pi over 2 again to get 3 pi over 2. And this one will hit its minimum value at -1. So the curve looks about like this as points. And as a curve, this might not be my best sine curve, but this will do the job. Whew, that's a little rough, but let's pretend that's a perfectly drawn, nicely symmetric sine curve, and we'll go off of that. Doesn't have to be perfect on your homework either. So with the graph in, or sorry, question first. Oh yeah, it is 0. What in the world did I do there? That could explain why my graph looks so wonky here. Let's see if we can fix that. It should be 0 right exactly here and -1 at 3π/2. So off to a good start, but then it went sideways right here. Thanks for that correction, Danny. Then at 3π/2, it hits -1. Oh, I think I know why I confused myself. I was imagining that was like a 2π, so I was expecting it to wrap back around like a whole sine wave. This is only a portion of a sine wave, so it should look more like this. Comes up and around, and it does have a better shape, and though it kind of broke down around here. That's our more accurate sine wave. Thanks again for fixing that graph. Other questions so far? Okay, next thing we can place here is, well, it's already placed. The limits of integration go here and here. Think of the 0 as your lower limit. Lower limit is the 0, and the 3π/2 is going to be the upper limit. So what we're really calculating here when they say find the Riemann sum with 6 terms, we're calculating this. Well, we're approximating it, is probably better said. It's the definite integral from the lower limit of 0. When we write these, we think of smaller number and then bigger number. That's not required, but that's what's typical for these kinds of problems. So from 0 to 3π/2, then we have to grab our integrand. That's sine x. We just put it inside the integral function. Let me put it in as actual sine x. There has to be one extra symbol, the dx, to end the integral. So this is what we're calculating, but we're going to approximate it using the midpoint rule with 6 subintervals. So that's officially what we're doing right here. And this turns into really truly a section 5.1 problem at this stage. The real reason to do it again is midpoint rule is tough, and we're practicing the new notation, which is a good thing to do, I'd say. So next thing we need to calculate is our delta x. We need to see how these intervals are going to be spaced out. Delta x is going to be b minus a, divide by sample size n. So there's the formula first. Now we grab our values. B is the upper limit of integration, 3π/2. Minus a, that's the lower limit of at 0. Then the whole thing is divided by 6. So 3π/2 multiplied by 1/6 would come out as 3π/4 after multiplying and reducing. So that's going to be our width of all the subintervals that we're going to calculate. Next thing I'd probably want to do is let's place all those subintervals. X0 is already placed. It's the value 0. X1, all we'll do is add our delta x value. So we're up to 3π/4. X2 is at 6π/4, which reduces to the 3π/2. X3 at 3π/4 again, and we're going to get 9π/4. X4, we have to end at X6, and X6 has to be 3π/2. So that's how we'll tell if we made any kind of weird simple mistake. Add 3π/4 again to this, it's 12π/4. Oh, wait a minute, and 12π/4 does not make sense. That's 3π. Looks like I did something really weird here. Oh, I think I saw what it was. I tried to reduce this fraction quickly. That's not a good idea. It's good to take your time with these kinds of things, right? It's terrible when we're doing calculus and the fraction is what's killing us on the problem. So let me see if I can fix this here. Let's throw away that temporarily. Cancellation should have been divide by 3 here to get a 2 here. And then our problem becomes pi over 4. Felt right, but the numerator was way off on that. And we can tell once we're all the way up at 3 pi, we shouldn't have ended at 3 pi. We should have been at 1.5 pi. So let's give this another try. X naught is still okay, so we get partial credit for that for sure. And back to the drawing board. X1 is pi over 4. X2, we're adding pi over 4 to all the new quantities, so this is 2 pi over 4. To get a pi over 2, that seems a lot more reasonable. X3 is going to be 3 pi over 4. X4 is 4 pi over 4, resulting in just pi. And finally, well, not finally, we're almost there. We have 5 pi over 4 for X5. X6 is going to be 6 pi over 4. And that one does reduce to 3 pi divided by 2, which is right where we should end up here at the upper limit. So we've got all the boundary points, and we need all of those to get our actual nice representative sketch of this thing. So we did all this only because we're trying to draw this graph. So let's place these. Here is going to be our first point. This is pi over 4. Then it was pi over 2 to here. Next one was 3 pi over 4 in this location. Then at pi was 1 point. Then move over to the right, and this one is at 5 pi over 4. So now that we have all those, what we really wanted was the midpoints. So we can calculate those pretty quickly at this stage. First midpoint is x bar 1, and you can always go by this as a process. Up above, the formula indicates you can just average them pairwise. That will absolutely work if you have the time. And it's not a bad thing to do. If you average 0 and pi over 4, it'd be 0 plus pi over 4 divided by 2, or a pi divided by 8. The reason I'm not a super big fan of this is not bad to do it once and average to get a value, but you wouldn't want to do it again to get x bar 2. Just add pi over 4 to it. In fact, you can make this even nicer. Take your pi over 4, multiply it by 2 over 2. Now it's 2 pi over 8. And it's compatible with that denominator. So we're adding 2 pi over 8 to each one of our quantities. Next one is 3 pi over 8. Then 5 pi over 8. X bar 4 is 7 pi over 8. We only have to go up to 6. X bar 5 is 9 pi over 8. And X bar 6 is finally 11 pi over 8. Now the check on this one is, take a look at your 11 pi over 8. It should be right about here. So if we were to add, say, 1 pi over 8, we'd get 12 pi over 8, reducing back to 3 pi over 2. So a half of distance of delta x gets us to the final rightmost point right here. And those are all of our midpoints finally. So we have all the x bars. It doesn't hurt if you wanted to say average 5 pi over 4, 3 pi over 2 to see if we get the right value. If we did average these, adding them together would give us 11 pi over 4. Then divide by 2, it's 11 pi over 8. So same quantity, either way we look at it. Not a bad formula, but if you can find a faster way that's more accurate, I'd say stick with it. So finally, after all that information, really most of the work here is this unfortunate statement. I mean, it's important. It's good to see what's happening as we calculate these things, but that is a good amount of work. I only asked one question like these on the homework assignment. So starting with pi over 8, it's going to be right here. I won't be able to actually, well, maybe we can barely fit that in there. If you can't fit in the value, just put in the tick mark. It causes a height right here. And so that's going to be our first approximating rectangle. Then over here is going to be 3 pi over 8. Right at that point, go directly up until you hit the curve. And that's what's tricky about this. I don't go up from that point and hit the curve. It must be right at the midpoint. Then once you're up here, you grab this edge, make the rectangle go all the way to that point's height, and pi over 2 will go all the way up as well. So that's our next one down. Then it's just rinse and repeat. 5 pi over 8 here. Point goes all the way to the top. I had a feeling that might have supposed to be symmetric, but we're going off the sketch that we drew. So we'll let it stand like that. Then this one's 7 pi over 8. We go up here and we hit a point that goes through in this way. And so far, in our definite integral we're approximating, all of this is a positive area contribution. Over here, this will be the negative area, but we can tell already this is going to be a positive answer because we have much more positive area to account for when we go to write out this approximation. So next, 9 pi over 8 here. Drop a point down below and then draw through these edges. So now all that's negative area, and last one is 11 pi over 8. We get a curve, or excuse me, a rectangle going all the way down to here in the curve, connecting back to the far edge at 3 pi over 2. These diagrams definitely get pretty busy. If that happens to you, don't worry too much about it. I'll just squint really hard, and if it looks about right, you'll get full credit for it. But now that we see it, let's calculate it next. Any questions so far, folks, to this stage? Okay, so now we're back to the definite integral. It's going to be approximated through m6. And now the formula for m6 will be, first throw in our delta x. Then we'll take f at x bar 1, f at x bar 2, plus f at x bar 3, f at x bar 4, f at x bar 5, and then plus f at x bar 6. So that's the official formula. All we're going to do is drop in our information. The function f is referring to the integrand sine x, so we're going to write sine for every one of these. We have our x bars over here on the right, so we'll plug those in as well. And so finally, delta x, let's look up at that value. It is pi over 4. I won't use the 2 pi over 8. That was just to simplify a different computation. So pi over 4 goes here. Now we go back to f of x, which is a sine function. And we'll do sine at x bar 1. So pi over 8 here. X is going to be sine at 3 pi over 8. Plus sine at 5 pi over 8. Plus sine at 7 pi over 8. Just an odd connected fact with all this. If you really wanted to, you can calculate to every one of these exactly, but it's of limited value. You still would want to know the approximate answer. Then plus sine 9 pi over 8. Plus sine 11 pi over 8. And finally, that's the last one. Once we get to this stage, we have to do the last slightly unfortunate task of import all of that into a calculator and get a value out. If this was an exam question, I would encourage you, just stop right here. You have the right answer. I'm not as worried about on an exam, you importing all this into the calculator. I know everyone can do it, and probably I would make a mistake if I tried to do it in an exam, timed exam setting. So let's make this comment here. I'll mention it again on the real exam. Stop here on exams. What I care about the most on exams is the process and this line right here. But for homework, we really should calculate it, and we should definitely do it just to see if we're right. We're expecting a positive answer. It's not going to be positive by much. This is a significant amount of negative area. So let's see if we really get that positive answer. I would encourage you to do something like, say, Desmos for this process because it's so tedious. You need something that's going to code up your function and do it in a slightly better way. Not doing for loops or anything like that. But at least define your function, f of x, as sine x. Then come down below, and now you can just type this out. Pi over 4 You could go sine right here, but it's even faster to go f at pi over 8. This is a little bit less typing. Now we're just a little bit more accurate, probably. F at 3 pi over 8. F at 5 pi over 8. F at 7 pi over 8. 9 pi over 8. I really should have calculated this before class, but you have to do it on the homework too, so this is a good thing to show. And here's the last one, f at 11 pi over 8. Close that last parenthesis, and I was expecting a number. There's a caution somewhere. Oh, I think they are expecting a parenthesis rather than a bracket. Close that last parenthesis. Oh no, and don't do that. Control Z does work on this. And that's that number I was expecting, a 1.02. So the definite integral of the sine curve, approximated with midpoints at 6 intervals, it's about 1.02 altogether. That looks very plausible for this. And our goal is, again, we'd rather calculate this exactly, but we're only just getting there. For where we are currently, I would say the bigger takeaway of this whole problem is getting used to that right there. I would say that's the big thing that we want to take away from this as well in the homework assignment. Any questions so far, folks, with doing that first approximation? Yeah.
So did you put that answer, the 1.02 where the M6 is?
Yeah, you could absolutely go M6 equals the 1.02 on this problem. Absolutely. And it kind of was conveyed that this equality right here was coming back from the M6, so it was kind of connecting as well. But yeah, I agree. It's good to also just emphasize that's what we found on this problem here. Other questions so far? Okay, well, we did our second midpoint rule. Those are always slightly unpleasant. There's a lot of steps involved in that. But what we're going to do next is look at a faster process for this kind of stuff. The midpoint rule is not bad. It's really efficient in the sense that you get great approximations. But if we're taking the limit as n goes to infinity, you have to really ask yourself the question, do we care at how well we approximated at the intermediate steps? Turns out we don't care at all. We just care that the limit here exists as n goes to infinity. So whether you're taking, say, left endpoints, right endpoints, midpoints, or if you're doing this, just taking arbitrary points, it's all going to turn into the same thing as the limit as n goes to infinity. When n goes to infinity, the widths of those rectangles converge to 0 as a width. And it's because of that, it turns out the right endpoint rule, Rn, if all you care about is writing down the limit for this is a really, really fancy formula to use. It says if any endpoint rule works, use right endpoint rule. It's the easiest one to specify. The right endpoint rule is actually just this. Take your f of xi, multiply by delta x. Delta x is the same formula, and xi's are specified in this way right up here. So what we're doing with these next examples, 3 and 4, is connecting back to the start of class today, doing these kinds of concepts. These sort of concepts appear on final exams, but I won't necessarily ask every single one of these problems you see here, but definitely expect something about continuity, something about differentiability, and then way down here, one of these two might be on the final exam as well. So let's take a look at how it goes. We're definitely going to need theorem 4. And this one starts by saying, express this limit, that awful looking thing right here, in the form of an integral on the closed interval from 1 to 7. Then a couple follow-up questions, where its lower, upper limit, and what is the integrand. So what we'll do is start by taking limit n goes to infinity. It's a summation as I starts at 1, our index, and ends at an index of n. That index n changes as n increases in the limit. Then we have xi, natural log xi cubed minus 1, and a delta x. So all I've done is copy the function. I made no actual progress here, but it really is progress because we're looking at each of the individual parts. What we're doing next is we're taking this and we're using the formula going right to left. That always seems strange. We're reversing something, it feels like. And here's how the reversal goes. It's going to turn into a definite integral. We need to put the numbers a and b here that are the right actual numbers. Anyone see what the lower upper limit should be? Good call. It comes right out of that closed interval right from here. So the 1 and 7 gives us a lower limit and upper limit. And in these problems, unless something otherwise has been specified, we will always put the lower limit, the smaller number, down below into the lower limit slot, and the larger number up above into the upper limit slot. That's not a requirement, but that's the typical kind of problem you'll see. We'll see where it reverses and what to do about it in these notes later on. The next step we take is a critical step. Notice how it says f of xi. Well, when you go to the left, it just turns into f of x. That's all we have to do. These are right endpoints, these xi's. We write it in as x, natural log, x cubed minus 1. Just drop the subscript and you've got the integrand already. So that's how we go from this to this, or vice versa. And the last thing is just kind of silly almost. Delta x is a real object with an actual formula, but we go from delta x to something that's just a symbol, dx. The symbol dx is very much a symbol, just like the integral sign. It's a start and an end to what you're integrating, x natural log x cubed minus 1. Then the whole thing is over. That's a really fast kind of problem. The information they wanted was that lower limit of integration is 1, upper limit equals 2. And that's what they were talking about when they said, what is the lower and upper limit of integration? It would be those two values. They asked also, what is the integrand? Integrand is just going to be the thing, the function going inside your integral symbol. So f of x equals x natural log x cubed minus 1 is the integrand on that problem. Yeah, go ahead. Oh, good question. The lower limit was 2, the upper limit was 7. I'm not too sure what I wrote in there. It must have been a really fast micro sleep or something like that. Upper limit should have been 7. I wrote that in a weird way too. Honestly, it's really tempting to just fix that, and lower limit just feels nicer if we put it lower, and upper limit should have been a 7. Thanks for spotting that error right there. So those are the moving parts of this kind of process. And what we'll do in example 4 is check going the other direction. This direction is harder, as strange as it sounds, because we're expected to go even further than what we did on example 3. But before we take a look at that, any questions on that example 3? Okay, let's give this a try. Express the quantity, the definite integral from 1 to 5 x squared e negative x dx in the form of a limit. This one's tricky. It's actually quite a bit tricky, surprisingly. We're starting with the definite integral and writing out the limit of Riemann sums. That means we have to specify xi, we have to use that formula, we have to specify f of xi, and we need to specify delta x. Almost doesn't even seem fair because they didn't do it over here. They didn't say what delta x was. But in these kinds of questions, that's what they're trying to go for. What is the full expression of the limit when we put in all of the values? Here's how we'll start off. Just copy down that entire thing. Definite integral from 1 to 5. The integrand is x squared e power negative x. And we still want to throw in a dx there to make this completely notationally correct. Now, the first thing I'll do is go and write down this step by the red dot. It'll be equal to the limit as n gets larger and larger, heading off to infinity, of a summation as the index I goes from 1 to, oops, that's not quite right, 1 to n. So it has to be a finite n right here. It seems like you could throw away that infinity, but that would really be a different concept. Then inside is going to be xi squared e to the power of negative xi. And last thing is delta x. So what I've done in this step is, it's just the same as example 3 by the red dot, going from the answer to the left and getting that Riemann sum. But here's where the next steps come in. Again, for this particular problem, there's a lot more expected out of nowhere. Let's call this step 1. Now for step 2, what we need to get is delta x. Formula is going to be b minus a divided by n, but we can't specify n because we're taking a limit involving that value n. But we can still go to our value b, that's the upper limit here, take 5 minus 1, divide by n, and we're dealing with a 4 over n for our delta x. Then let me scroll up here just so we can see this formula better. Okay, we'll tuck it away there where it won't cause too much trouble. So we've got the delta x in the process. For step 2, or excuse me, we're on step 3 now. Next thing we definitely want to calculate is this object, xi. These are all of the right endpoints on your Riemann sum. So xi is going to be equal to, it says first take your lower limit of integration a, that's going to be the one in our problem, add to it. Notice there's an index I, and the reason for that is you get to xi by adding delta x I different times to get to that value. So that's how we got to all of our boundary points. We just repeatedly add delta x, and that's what this multiplication by I is saying, add it I different times. So an I is going to stay in the problem, that index. We multiply by delta x, but we've calculated that delta x is 4 over n. So we've got our xi, and now here's where step 4 puts it all together. This will be our official answer. It's a limit as n goes off to infinity, summation I goes from 1 to n of, where we see the xi, we're plugging in this as a formula. So it becomes 1 plus I times 4 over n. And we can call that 4i over n. That's a small simplification there. And over here, it's going to be a base e exponential multiplying negative, and then same value. It's xi, so we come down and look it up from step 3. 1 plus 4i over n. And then last thing, we have to throw in our delta x. Delta x was 4 over n, so it multiplies right here, times 4 over n. So that's our final answer. This integral here, if we wanted to calculate it directly, we would have to evaluate to that limit. That is a really, really bad limit to try to calculate. In fact, if we try to calculate that limit, we might just say maybe an approximation is a better answer. And then we might as well come back here and use a midpoint rule to get our approximation. These are some amazingly hard limits. And what's even worse is change the function a little bit, and you might need a method for this one. Change it a tiny, tiny bit amount, and it's a totally new ad hoc method for your new function. A new method practically for every single function on this thing. We need a better way to calculate these limits, and that's what section 5.3, Fundamental Theorem of Calculus, is going to be all about. But any questions at all, folks, so far? I'm just writing it down. Yeah. Oh, good call on that one. I think I just dropped it. So that squared there. Let me put this in purple to make it show. It should have been here as well. Thanks for spotting that value. That's not a good one to drop there. Now the limit is probably a little bit harder, but it's at least correct. Thanks for seeing it. Other questions so far? Okay, so that's converting between different limits. And with what we'll do with the last time of our notes is coming down here. Let's take a look at this theorem once again. I'll let example 5 be our last example for the day. I definitely do want to finish off these last properties of integrals because they are important. So when we come back to class on Thursday, we'll be right here taking a look at these properties. Let's spend some time with this theorem 3 again. It's been restated here. It tells us if f is continuous on a closed interval from a to b, or if it has only a finite number of jump discontinuities, then it will be integrable on a to b. So now if we look at this function, the integral from 0 to pi of tangent x dx. When we have the fundamental theorem of calculus, this becomes extremely dangerous as a problem. The fundamental theorem of calculus tells us to just find an antiderivative and evaluate it at the upper limit minus its evaluation at the lower limit. But you cannot do that unless you know it really was integrable in the first place. If it wasn't, well, no one stops you from getting an antiderivative, but your answer is going to not match the problem at all. It's going to be nonsense. So when you look at a problem like this one, it's always a good question to ask yourself, does it even exist? Existence is going to deal with continuity, so the question now turns into, is that function continuous on the closed interval from 0 to pi? So let's write this out again. Is f of x, which is equal to tangent x, which is sine x over cosine x, continuous on 0 to pi? Turns out the answer to that is no, this is a very discontinuous function. Tangent has infinitely many discontinuities. Anyone happen to see what the problem would be in that interval? Well, it wouldn't necessarily be the value of pi itself, but you're on the right track. Cosine has a problem. It's going to be at pi over 2 where we have an issue. At pi over 2, we take value 0, and that's right inside of our integral. So this thing right here, 0 to pi, tangent x, dx, does not exist, since tangent x is not continuous on 0 to pi. And the issue is not that it has a jump discontinuity, it's a vertical asymptote. It has an infinite discontinuity and infinitely many different ones. But exactly what in our interval is all it takes to cause a problem. If this was 0 to pi over 4, it would exist as an integral. But include a discontinuity, and we have a massive problem with it. Well, any last questions, folks, with that quick example there? Okay, I think this will be a good stopping point for us then. When we come back, we'll finish off these notes, and then we'll be looking at the fundamental theorem of calculus. So that will be exciting. The hint or the preview to that is we'll be looking at antiderivatives really closely so that we can do that limit in a reasonable way. That's a terrible looking thing to try to do directly.